All right, so let's get going. So, what we're going to be doing today is we are going to wrap up our look at correlation. And by wrapping up our look at correlation, what I really mean is this is the last time we're going to focus in on correlation and just correlation, because as you've begun to notice more and more, as we develop these skills and these techniques and these concepts that we see in statistics, they carry forward and they're used as we continue on through statistics. So mean, standard deviation, correlation, all of these concepts are going to be carried forward. But today will be our final look at just correlation. And then we're also going to start our look at probability, specifically some basic rules of probability, so we can lay that foundation, see why it's important to have knowledge about probability, such as conditional probabilities in psychology. And then hopefully that will lay the foundation for next time when we meet, and we're going to think about and illustrate how to think about probability not as a mathematician, but as a statistician. So those are two very different uses of probability, and we're going to see that. But first, we got to lay down those foundations. So today, what's on our schedule is we are going to wrap up our look at correlation by taking a look at the limits of correlation, specifically the limits of Pearson's correlation coefficient that are, by taking a look at a really interesting study on assertiveness and leadership and what is the relation between how assertive somebody is and how good of a leader that person is. And then we're going to take a look at some probability basics, and we're going to revisit the marshmallow test for those, because as we're going to see, it's a really, really good example of conditional probability, which sometimes tends to be confusing when you first start thinking about probability. So hopefully, if you can see how it's actually applied to a real psychology study that we've already introduced, hopefully that will be an easier stepping stone to get to the point where probability is just locked in and makes sense. So I know we've mentioned this a few times already, but probability does fall into that category of level up moment here. So again, there is a lot of terms going on in probability. There's a lot of concepts in probability. As we move on, you're going to see that some of those are more important than others, and that's what we'll focus on in this course. However, just know that, especially in chapter 4, there is a lot of stuff that's thrown at you. So this is one of those chapters where it is perfectly understandable that you will not get everything the first time through. So try to do as best as you can. And then as you move forward, as we continue to encounter probability, this one is more tailored. As we continue to encounter probability, you'll see that we encounter some probabilities more than other concepts of probability. And if you're still confused on those concepts that we're going to encounter later on, highly, highly recommend go back to this meeting, go back to chapter 4, come by an office hour. We can work through it. We can take a look at it in different ways. But just know that you need to get solid on those concepts, especially when you encounter them later on and you realize, oh, I don't understand conditional probability. And now here we are doing statistical inference, and all of a sudden conditional probability is important. It's totally fine to go back, revisit it, and get that stamped in. And today we are going to continue our ComRom, but we're actually not going to have any do it with me demos today. So a lot of what you're going to see today has been done with Excel, has been calculated with Excel. But this is going to be a day where we're kind of on our own and our computer is going to be a little lonely, but it still loves us. It still wants us back. So remember that when we're doing our homework, even when it's simple, try to do the calculations in Excel, try to get that muscle memory in there, and don't disregard your ComRom for too long. You got to feed that relationship. All right, so leadership and assertiveness. So this is going to be, we're going to take a look at a study that basically wanted to know how much assertiveness does it take to make a good leader, right? So assertiveness is a quality that different people vary on. So some are very low in assertiveness, some are very high in assertiveness. And it's a valid psychological question and a very interesting psychological question, especially for people who I hope eventually do become leaders in whatever field they choose. How much assertiveness is the best amount? Should you be as assertive as possible? Is that what makes the best leader? Should you be unassertive? Is there some sweet spot in the middle? That's the kind of relationship that Ames and Flynn were looking at when they did their study, What Breaks a Leader? The mystery word relationship between assertiveness and leadership. So we're going to take a deep dive into this study as our last look at correlation. So let's just set this up, and I'll read a little bit from their procedure that they did. So the first thing that they did is they got a leadership score. So they recruited a whole bunch of subjects, and these subjects were from a business school. And then what they did is they got a leadership score by basically asking other people, how good of a leader do you think this subject was? So participants collected feedback on their leadership behavior from several former coworkers as part of an organizational behavior course. So this wasn't a self-assessment of leadership. This was actually asking other people that they had worked with, how good of a leader do you think this person was? And they would ask them, so respondents were asked, that is the coworkers were asked via an online survey to provide ratings referring to 4 domains of leadership: motivation, social influence, managing conflict, and working in teams. So they got a multidimensional rating of how good of a leader these people were. So that was the quantitative variable of leadership. So if the respondents thought that these participants were amazing leaders, just amazing on motivating their team, amazing on influencing using social skills, amazing on managing conflict, and amazing on working in teams, they would score very high on that quantitative variable of leadership skills. On the other hand, if these leaders were poor, couldn't motivate their team, had no influence, couldn't manage conflict at all, maybe even made conflict worse, and did not know how to work in a team, they would score very low on this quantitative variable. So that was the leadership measure. And then what they did is they also had a measure of assertiveness. So the study also included the TKI, and that is the Thomas Kilmann Conflict Mode Instrument, which assessed coworkers' perceptions of the participants' level of assertiveness. So once again, the coworkers were given a survey, and this measured how assertive they thought that the participants were. So in both of these measures, it was somebody else who had an experience and a previous encounter with the participants that was judging whether or not they were good leaders, and was also judging whether or not they were actually assertive. All right, so is there a relationship between those two variables? Is there some sort of increase, decrease relationship that they have between each other? So to do that, we're going to take a look at this graph here. And first thing I'll point out, let's zoom in a little bit. First thing I'll point out is that the legend there has the scores for, if we start at the bottom, teams, how good are they at working in teams? Conflict, how good are they at resolving conflict? Influence, how much social influence did they have? Motivation, how good were they at being motivated? And then the top thick line is overall. So foreshadowing on this, the first thing I'll mention is that literally all of those measures were almost exactly the same. So they did measure 4 things, but in general, everything just overlapped. So it's almost as if there was just one measure. So we can focus on that overall line. Now, in terms of the graph, in terms of the results of this study, we have assertiveness down here. And assertiveness, they have that unit of a z-score on there. So we're going to delve into z-scores in a little bit more detail later in the course. But for now, all we need to know is that the higher the z-score, the greater the assertiveness. And the lower the z-score, the lower the assertiveness. Just to give you a little bit of a spoiler on z-scores, 0 is always the mean of a z-score. So if you scored 0 on assertiveness on this scale, that means that you had the average amount of assertiveness. And then every step above that was increased assertiveness. Every step below that was decreased assertiveness below that average level of assertiveness. So that's the assertiveness score. That's on our x-axis. On our y-axis, we have our leadership rating. And the leadership rating is, again, on a z-score. And again, a 0 means that you had a leadership rating that was the average for this particular study. And then higher scores means that you were rated higher as a leader. Lower scores means that you were rated lower as a leader. So those are our axes. And then what they did is they plotted for every single participant where they were on these two axes. So they made a scatter plot of the data for these two quantitative variables. And before I show it to you, if I was going to fit a line of best fit to this data, if I was going to calculate a correlation coefficient and then draw that line so that the dots are pretty much symmetrically oriented around that line, then the line that I would draw is this line right here. So that is the line of best fit. I'll show you the data in just a minute, but that is the line of best fit. And if you look at this line and you look at this correlation, you say to yourself, well, that's a negative correlation, right? The line is sloping downwards. That means that there is a negative relationship between these two variables. In other words, these variables change in opposite directions. So as assertiveness goes up, leadership ratings actually go down. So that is really surprising because you might think to yourself, well, most of the good leaders that I've experienced actually have more than a typical amount of assertiveness. And I can imagine that the more assertive you are, maybe the better leader that you should be. So this is actually quite confusing. And the reason that is quite confusing is because it's actually incorrect. And this is another great reason why you always look at your data. If there's not just one thing that I want you to take away from this course, but if there's 7 things that I want you to take away from this course, one of them is always look at your data. Because when we get into statistical packages like Excel and like SPSS that we'll take a look at later in the course, they will calculate that line for you no problem. And they will do it and do it correctly and crunch the numbers the way that they're supposed to be crunched. And you would walk away going, oh, hey, assertiveness goes up, leadership goes down. What a surprising result. The reality, though, is that's not the case. And as soon as you look at the data and see that it looks like that, you immediately can see the problem. And the problem is that the relationship between assertiveness and leadership is not linear. And the correlation coefficient that we've used to introduce correlation, the Pearson's correlation coefficient, that is for linear relationships only. And we know that it's not linear because as we look, well, first visually it doesn't look linear, but if it was a little bit more scatter, let's say, if you see any pattern to the dots that are above the line and below the line, as you go along the line, that means it's not linear. So almost all of the dots are below the line in the early going, and all of the dots are below the line at the end. But all of the dots are above the line in the middle here. That kind of a pattern means that it's not linear. So what we have here is not a negative correlation at all. What we have here is actually a curvilinear relation. So a curvilinear correlation, you can compute that. So you're not completely on your own. If you ever notice a curvilinear correlation, you don't have to throw your hands up and say, well, we can't compute that, that's curvilinear. There are tools for that. They go beyond the scope of a statistics course. If you continue on into grad school, you will learn how to calculate that curvilinear correlation. But for this introduction to statistics, what I really want you to know is that if you have a curvilinear correlation, a relationship between variables that is clearly on a curved line, you cannot use Pearson's correlation coefficient. You cannot use that R. Because what we have here is we have a very strong relationship. And that relationship is that as assertiveness goes up in the early going, so too does leadership. So in the early going, the more assertive you are, the better a leader you are. And then we get to this point here where as assertiveness goes up, leadership doesn't really change. So there's this kind of sweet spot where it sort of levels off, and you can increase assertiveness and your leadership skills, or your leadership rating in this case, doesn't change. But then as assertiveness increases, then we get a huge negative correlation and leadership skills go down. So rather than having a negative correlation between assertiveness and leadership rating, what we have here is we have a curvilinear relationship that says you need a certain amount of assertiveness, but if you have too little, you're not going to be rated very high as a leader. If you have too much, that's even worse. If you're overly assertive, that's even worse, and you'll be rated even lower as a leader. But there is that sweet spot in between where leadership is rated as the highest. All right, so any questions on the curvilinear relation and why we can't just go ahead and fit a linear correlation to that? All right, so again, the title of this was What Breaks a Leader? The curvilinear relationship between assertiveness and leadership. And the thing to remember for this is that, number one, you cannot just go forward and fit a linear relationship or a linear correlation coefficient and calculate that when your data is clearly not linear. And secondly, Ames and Flynn would have had no idea that their data was not linear unless they did that scatter plot, unless they graphed it. So always graph your data, just visualize it, and it'll lead you to insights that can contribute a lot to psychology. Speaking of insights, it is now time for surprise callback. So as I was going through making this meeting today, and I saw that result of that kind of sweet spot of assertiveness, it reminded me of another study that we previously took a look at, which was the in-your-face facial metrics predict aggressive behavior in the laboratory and in varsity and professional hockey players, because aggressiveness is not assertiveness, but I think we can all agree they're sort of adjacent concepts, right? They're not exactly the same, but they're kind of related. So this was the study that we took a look at that was trying to answer the question of whether or not your face shape can predict aggressive behavior. Or in other words, is there a thing as resting a face? And if you remember, we used this example here to take a look at histograms. And when we took a look at that data there, and we said, all right, well, let's unpack that data and let's see what is the distribution of aggressive behavior. We made this histogram over here. And you might recall, I definitely recall that during the class meeting, I noticed that in the shape of this distribution, there seemed to be a spike right there. So there was a lot of the distribution was in the 100s and the 200s, 250s, and then there was a drop off, but there seemed to be a spike there at around 450, and then another serious drop off all the way to 600. And I asked the question, well, why is this spike there? Maybe there's a evolutionary advantage to it. Maybe there's something that is beneficial to having that much aggressiveness, like more than the average, but not too much aggressiveness. And from this histogram, and then looking at the data from the Ames and Flynn study on assertiveness and leaders, it occurred to me that maybe the reason we have this spike in the frequency of people with that aggressive behavior score is because these are the people that make the best leaders. Maybe people with this much aggressive behavior are typically the people that have this much assertiveness. And that's why we see that little spike there in terms of the number of people with specifically that amount of aggressive behavior. Now, just to point out again why it is so important to look at your data. Oops, surprise callback, not yet. This is a histogram that we looked at. And because of the visual nature of this, our minds, which are visual processing machines, notice that little spike. and remembered that little spike in a way that we wouldn't if we looked at a table of data, in a way that we wouldn't if we looked at raw data, and it put it away in our minds. And you hardly ever forget a picture. A picture is like a face, right? You might meet a person and forget their name, but how many of us always say, oh, you know what? I never forget a face. I'm sorry, I don't remember your name. Well, I never forget a graph. I'll forget a table, but I'll never forget a graph. So I had this stored away, didn't even know it, and then saw this and said, hey, wait a second. Maybe those two are related. Maybe the aggressiveness and the assertiveness are somehow related, and that's why we got that spike. Anyways, just as a sort of aside for your future as psychologist, that's one of the places where these ideas for research, these ideas for projects, these ideas for interventions comes from. It comes from just these connections that happen as you encounter more and more psychology. And if you put the data and the concepts into the right communication method, which for human beings is often a visual depiction of the data, your mind itself will start making those connections, and you're more likely to make a big contribution to psychology as a result. So that was my surprise callback. Surprised myself that that sort of fits so nicely. And again, this is research. We might do an experiment on those two and find out that I'm completely off. But again, those ideas, those connections are much easier to come by if you take a look at your data. All right, any final correlation questions before we wrap up that section? All right. So now we're going to take a look at what is probability, just the real basics, beginnings of what probability is. Probability, just so that you know going forward, is very important to statistics. Inferential statistics, especially taking a look at a sample in an experiment and generalizing to a population as a whole, is where the power of psychology comes from. Because if you run a study on 20 people and you can't generalize to the population, then you can help 20 people instead of helping 7 billion people in our world. So inferential statistics is what takes us from the 20 to the 7 billion. And part of inferential statistics is probability. And that's why we're going to be focusing in on that before we get to inferential statistics, so we can build those foundations. All right, probability basics, super basics. We'll start with the definition of probability. The probability of any outcome of a chance process is a number between 0 and 1. So that's the first thing to highlight. Probabilities go from 0 to 1. 0 is it never happens. 1 is it always happens. And then the number in between tells you how likely it is to happen. So that number between 0 and 1, that describes the proportion of times the outcome would occur, and this is the key that I want to drive home today, in a very large number of repetitions. So again, it's a number between 0 and 1 that describes the proportion of times an outcome would occur in a very large number of repetitions. So if we were able to do any event over and over and over and over again, what is the proportion of times that a particular outcome would occur? So you can think of some classic examples, things such as flipping a coin. So we know that when you flip a coin, the probability of heads equals 0.5. Again, 0.5 is the probability expressed as a number between 0 and 1. So that is 0.5 or 50%. And we're going to get into some formulas today. So once again, remember, you never read this as p heads equals 0.5. Always read this as the probability of heads occurring, you can add the occurring in if you like, equals 0.5. So again, on this one instance, your coin is either going to land heads or it's going to land tails. However, if you are able to flip this coin over and over and over again across a very large number of repetitions, you would find that half of those outcomes were heads. And that's why we say the probability of heads equals 0.5 or 50%. All right, another example, the probability of rolling a dice and getting a 2 equals approximately 17%. So this formula, we're going to see formulas for probability. The formula for a probability, if you're thinking about it in mathematical terms, is how many outcomes are the ones that you're looking for. In this case, we have one outcome, it's rolling a 2. How many outcomes are possible? In this case, we have 6. It's a 6-sided dice. 1 divided by 6 equals approximately 17%. But importantly, if we were rolling this dice over and over and over and over and over again, and then we counted up how many times did it occur that this dice rolled a 2, and then divided that by the total number of times that we rolled it, we would find that 17% of the time the dice came up as a 2. So the probability of rolling a 2 is therefore equal to 17%. All right, and just one last example. If you were playing roulette, the probability that you would get a 3, that the ball would land in that 3 pocket is 0.026, and that is 2.6%. So another thing to remember about probabilities is that they're expressed between 0 and 1. So this 0.026, very close to 0. It's very unlikely that you're going to win on any single roll of a roulette wheel. But again, this is the long run probability. So the probability of getting a 3 is 0.026. If you are expressing that as a percentage, you would simply multiply it by 100. Be very careful when you're doing that, because sometimes that decimal place tends to get a little wonky, and students will misplace a decimal place. I've seen it done a lot of times. I don't even want to think about the long run probability of it. But again, in this case, if we spun this roulette wheel over and over and over and over again, we would find that 2.6% of the time it came up and landed in that 3 pocket. And then just to kind of give you an example of why casinos make money off of roulette. The reason they can make money on this is because the wheel looks like it's all black and red. So a lot of people think that the probability of red or the probability of black would be 50%, because half of the wheel is black and half of the wheel is red. But if you notice, there are always at least one slot. And in America, there's 2 slots that are green. So your probability of the ball landing in a red slot is actually 0.47. And that difference between the 0.47 and the 0.5 in probability, 47% versus 5%, is where casinos make their money on roulette. All right, so we're going to take a look now at a demo, just real quick, in online about long run probabilities and how to think about probabilities and kind of visualize what these things are, just so we can see what we mean by proportion in a long run of events. This is what I want to get to. So let me zoom in on this so that we can see the graph a little bit bigger. Okay, so this is the idea of probability. This is going to be a nice visual representation of what we mean by probability is the proportion of times an outcome would occur in a very large number of repetitions. So we're going to show here, or we're going to take a look at the probability of heads occurring in a number of coin flips. So we'll zoom in on this just a little bit more so we can get that nice and big. All right, so this is our graph here. And down here on the x-axis, we have the number of flips. And up here on the y-axis, we have the proportion of heads. And this is going to be the proportion of heads so far. So it'll show the proportion of heads after 1 flip. It'll show the proportion of heads after 2 flips. It'll show the proportion of heads after 10 flips. And we're just going to be flipping the coin down here. So again, probability of heads as a decimal is 0.5. And we're going to start off with 1 flip. And what this is telling us now, we have this little dot over here. It tells us that the number of flips equals 1 and the proportion of heads equals 1. So if we were to calculate probability as a proportion of times an outcome would occur in a very small number of repetitions, then we would say, oh, the probability of getting heads on this is 1. It's 100% because it occurred 100% of time. However, probability is that idea that we're doing this over and over again for a long run. So we can do it again, we can flip it again. And as we see, now we got tails. So now we have number of flips 2, proportion of heads equals 0.5. And we can flip it again. And now we got tails again. So we have 3 flips and we only got 1 out of 3 heads. And we flip it again. And now we got heads again. Flip it again, we get heads again. Tails, tails, heads, 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 heads. Incidentally, we're going to cover this in a future meeting. Humans are very, very bad at detecting randomness. So we got 1, 2, 3, 4 heads in a row. Our minds at this point are telling us that this might not be random. And that's one of the reasons why people develop superstitions, is because they see causality in random occurrences. And it's another reason why in sports, people will go on hot streaks or they'll go in slumps. So if you watch any sport, especially baseball loves its statistics, commentators will always say, oh, John Smith is on a 4-game hitting streak, quite the hot streak. Or, John Smith hasn't had a hit in his last 8 at-bats. He's got he's on a cold streak there. They've done statistical analyses on these to find out that hot streaks and cold streaks are just random variation. There's no actual ability that goes into it. It's just the fact that when you step up to the plate, it's a random occurrence. And as many hot streaks and cold streaks would occur as you would expect just by random. So we've had 2, 3, 4 heads in a row. Let's see what happens next. 5 heads in a row. One more time. 6 heads in a row. 7, 8. How high can we get it? 9. See, I know probability, and even in my mind right now, I'm thinking to myself, did I break the computer? Like, did I do something to the program? All right, we got 9. 10. All right, we couldn't get 11. 10 in a row, though, that's quite astonishing. And you might say to yourself, well, doesn't this kind of disprove what we're talking about? It doesn't, because we're talking about very large numbers of repetitions. So up until now, we only have 18 repetitions. Probability does not care about your short runs. Probability only cares about very large numbers of repetitions. So what's going to happen is we can keep flipping this. And like a homing missile, that proportion is going to get closer and closer to that 50%. Because over the long run, the probability that you're going to get a heads is 50%. So the proportion of times that an outcome occurs, that heads occurs, over the long run will be 50%. And if we keep going, you'll see that we get back closer and closer. And importantly, we may never get to 50%, but in the very large number of repetitions, we will approach that 50% every single time. So regardless of what universe we live in, that heads will eventually get down to 50%. Incidentally, this is the least random that I've seen this simulation and all the times that I've tested it. So of course, when I'm doing it live, it would appear to be the least random. But if you do want to try this, the link for this is available in your textbook. And then the other thing that you can do is if you really want to see what happens in a very long run, I mean, here we're still only at about 124. You can go down here to number of flips. You can put in something like 1,000 flips, tell it to flip. And now you can see that over 1,000 flips or over 1,000 flips, what's the proportion of heads? We're at 0.495. And if we went to 10,000, we'd probably be even closer to 0.5. And again, that's the idea of probability that we want to think of as statisticians. What is that proportion of occurrences over the long run of a particular event? And then also, this is one of the reasons why it's very difficult for our human minds to understand it, because when we went 10 heads in a row, that really seemed like a hot streak to me. But again, that was just probability being probability and saying we don't care about your short run, a small number of repetitions. We're only a large number of repetition concept. All right, any questions on that? All right. There we go. Okay, so that's the basic idea of probability, that proportionate time something occurs in a very large number of repetitions. And then we're going to spend the rest of today looking at another concept of probability called conditional probability. And the reason that we're looking at conditional probability is because this is one of those probability concepts that intuitively we often make mistakes with. And intuitively, we often think that two events are linked when they're actually not linked. So it's one of these concepts that counters our intuitive expectations. So sometimes it's a little hard to grasp. So I wanted to make sure that we covered it today. So conditional probability, the probability that one event happens given that another event is known to have happened is called a conditional probability. So it's a probability of something happening when you already know that something else has happened. So you have extra information, and now you're wondering how much, what is the probability that this other event is going to happen. So the conditional probability that event B happens, given that event A has happened, is denoted by probability and then in brackets B given, that's that up and down bar A. So P bracket B up and down bar A bracket, read that as the conditional probability, or just the probability that B occurs given that A has already occurred. So probability that B happens, this line here is given that A has already happened. And as we're going to see, sometimes the probability that B happens changes because A has already happened. And sometimes the probability of B does not change at all because A has already happened. And it's important to know which of those is true, especially in doing psychology. Because concepts in psychology, for example, concepts such as risk factors are conditional probabilities. What you're saying is that the probability of you developing this mental illness, given that you have encountered this risk factor, is greater than the probability if that risk factor did not occur. So risk factors like developing alcoholism, if you have an alcoholic parent, that's a conditional probability. So as psychologists, it's very important to get this concept down so that we know exactly what we're dealing with when we deal with those ideas of things like risk factors. Now, very thankfully, we have ourselves another connection back to something that we've already encountered. So we're going to go back and revisit the marshmallow test to take a look at conditional probability and how it's related to predicting an outcome given your knowledge of another event occurring. So going back to the marshmallow test, going back to the data that was in Mischel and Shota and Peek's work, and we are going to take a look at first the relationship between the ability to delay and academic competence. So is there a relationship between those, and is the conditional probability of academic competence given delay actually change? So to answer that question, to kind of illustrate this, we're going to start off with a non-conditional probability, which is simply the probability of academic competence being greater than or equal to 100. So this is what I mean by, we're going to get into some mathematical notation here. So again, P for probability, academic competence, or ACAD comp for academic competence, greater than or equal to 100. This is simply asking, in this experiment, for the students, for the adolescents that they study, what is the probability that any of those has an academic competence score greater than 100? So how can we visualize that? How can we understand that? So here we're going to have a scatter plot of every single one of those 87 subjects. And we are going to plot them on this graph, and we have delay down here in minutes. So when they were 4 years old or when they were 5 years old, when they did the initial experiment, how long were they able to wait before they rang the bell and had that one marshmallow? So that's on the x-axis there. On the y-axis is the rating of academic competence that their parents gave in the survey. So each of these dots is an individual subject, and the data looks like this. So we want to know, out of all of those subjects, if I was to pick a subject at random, if I was just to choose one subject there at random, what is the probability that that subject would have a score, an academic competence score of 100 or greater? So what is the probability that a subject is going to be above that line if I'm just choosing subjects at random? So in general, the mathematical formulation for this is that the probability of event A occurring equals the number of outcomes that are classified as event A over the total number of outcomes. So one more time, the probability that A occurs equals the number of outcomes that are classified as event A over the total number of outcomes. So when we're asking about academic competence scores greater than 100, what we want to know is the number of outcomes that are classified as academic competence scores greater than 100 and divide that by the total number of outcomes. So to write that out in more probabilistic mathematical notation, P probability academic competence being greater than or equal to 100 equals N, the number of subjects that scored greater than or equal to 100, all divided by the total number of subjects. So again, how many of these subjects satisfy the event, which is scoring greater than or equal to 100, divided by the total number of subjects, in this case, how many subjects were actually in the study. So for that, we need to know how many subjects were in the study. So basically, how many dots are in this scatter plot. And if you can recall, previously we mentioned that they were 87. So 87 subjects were in this study. So that is the number of events that we have. But not all of them scored above 100. So how many of them scored equal to or above 100? Well, for that, we need to count up the dots right there. So how many of them got at 100 or above 100? And that number is actually 43. And then we divide 43 by 87, and we can see that the probability that a single subject got an academic competence score greater than or equal to 100 equals 0.49 or 49%. So just randomly choosing a subject out of those 87, you have a 49% chance that the subject you chose had an academic competence score above 100. So far, so good? All right. So now let's get into conditional probabilities. So we just figured out the probability of randomly choosing a subject with an academic competence greater than or equal to 100. But what if we give a condition on that? What if we tell you another event that has already occurred? What if we tell you that we know that this subject waited longer than 10 minutes? So not just any subject, but this subject waited longer than 10 minutes. So now the question becomes, what is the probability of getting an academic competence score that is greater than or equal to 100, given that little bar there, given that their delay score is greater than or equal to 10 minutes. So what is the probability of getting an academic competence score greater than 100, given that we already know their delay ability was greater than or equal to 10 minutes? So does that have a different probability? So to do that, we just go back to our data, and we now have, and this kind of looks horrible, but it's not as horrible as it looked. I was about to say it's not horrible. These things start to get a little bit complicated, which is why, again, it's very important to read them out. So here we have, again, the probability of getting an academic competence score that is greater than 100, given that the delay is greater than or equal to 10 minutes, equals the number of subjects that were greater than or equal to 100 and were greater than or equal to 10 minutes of delay, and all of that divided by the number that were greater than or equal to 10 minutes of delay. And the reason we have the 10 minutes of delay up here and the 10 minutes of delay down here is because we know that has happened. That's what this given delay greater than or equal to 10 has happened. We're given the information, hey, the subject you're looking at, they waited for 10 minutes or longer. So what that means is instead of being interested in all the subjects, we are now only interested in these subjects over here. Those are the ones that we're focusing on because those subjects lasted 10 minutes or longer in the delay test. So we don't have to consider any of the other subjects whatsoever. And then once we do that, we can now just calculate this probability the same way that we did before. So to sort of fit it into what we're looking at there, the number of subjects that waited 10 minutes or longer, that's 25. If we counted up all the dots in that pink window there for 10 minutes or longer, 25 subjects were able to wait for 10 minutes or longer. And we're only interested in those 25 because we know we're limiting this. It's a conditional probability. And the condition is you waited 10 minutes or longer. And now we ask ourselves, out of those people that waited 10 minutes or longer, how many of them had an academic competence score greater than 100? So how many are in that window right there? And it turns out that in that window, there are 16 individuals. So now we have 16 individuals with greater than or equal to 100 academic competence out of 25 individuals that waited longer than 10 minutes. And we have a probability of 0.64. So if you choose a subject at random that waited 10 minutes or longer, you have a 64% chance that their academic competence score is 100 or greater. Okay, so as a synopsis of this first analysis here, we have the probability of getting an academic competence score greater than or equal to 100 in general, without a condition on it, but just in general, was 0.49, 49%. However, when you put a condition on it, that they were able to wait longer than 10 minutes, then the probability of getting an academic competence greater than or equal to 10, given that the delay was greater than or equal to 10, that actually equals 64.64, so 64%. So it's actually higher. You're more likely to pick a subject that has an academic competence greater than 100 if you restrict it to subjects that were able to wait longer than 10 minutes. And what this means is that academic competence and delay of gratification are not independent. So when your conditional probability is different than your standalone probability, that means that your two variables are not independent. Academic competence and delay of gratification, they are not independent because when you know delay, the probability of academic competence changes. And that means that these two are not independent. They are related variables. All right, any questions on conditional probability so far? All right. So that was for academic competence. You'll remember that, well, hopefully we remember that the parents of these subjects rated them on 4 different dimensions. There was academic competence, social competence, frequency of problems, and coping skills. So let's take a look at another one of those, and we'll take a look at the frequency of problems. So we'll do the same analysis. Now we have the probability. We're asking, what is the probability that the frequency of problems rating is going to be greater than or equal to 100? So what's that probability in general, given no other information? So once again, we go back to our scatter plot. This time we got delay once more on the x-axis there, but now we got frequency of problems on the y-axis. So once again, that was a rating by the parents. And we'll put the points up there. Each point is an individual subject with their delay in minutes and frequency of problems, determining where that point is. And we want to know, what is the probability that if we chose a subject at random, we would get somebody that was above that line of 100. So greater than a score on frequency of problems of 100. So the analysis is exactly the same. We have our formula. The probability of, in general, an event occurring, event A, equals the number of outcomes in event A, or that are classified as event A, over the total number of outcomes. So to translate that to this instance, the probability that we get a frequency of problems greater than or equal to 100 equals the number of subjects that scored greater than or equal to 100 divided by the total number of subjects. So it's the number that satisfy the condition divided by the total number, and that's how we figure out that probability. So once again, we have the total number. So how many dots are there? How many subjects are there in the entire experiment? That is still 87. And now we ask ourselves, out of those 87, how many scored higher than 100? So in this case, we count the dots and we get 46. So 46 subjects scored higher than 100. So randomly choosing a subject from this experiment, we figured out that the probability of getting a subject with a frequency of problems greater than 100 actually equals 0.53 or 53%. So that is the that is the probability of any random subject having a frequency of problem score greater than or equal to 100. So now we can ask ourselves, well, all right, that's the probability in general. Is that result conditional on delay? So we go back and we ask ourselves, all right, is the probability of getting a frequency of problems greater than or equal to 100, given that the delay was greater than or equal to 10 minutes? So what is that probability of the frequency of the problem being greater than or equal to 100? Once again, given that we already know, we've been told that this subject's delay was greater than or equal to 10. So that's a question now that is a conditional probability, conditional on delays being greater than 10. So once again, we have our formula up here. Once again, it looks rather gruesome, not gonna lie, but we have probability of the frequency of problems being greater than or equal to 100. Given that we already know that we're dealing with subjects with delays greater than or equal to 10 minutes, equals the number of subjects that satisfy both of those, greater than 100 and greater than 10 minutes, all over the number of subjects that just satisfy the 10 minutes. So that is the general formula for this conditional probability. Once again, we are only interested in subjects that we're able to delay for 10 minutes or more, because that is the condition that we put on this probability calculation. So we're only interested in those subjects there. We don't have to consider the other subjects at all. And once you do that restriction, it just becomes exactly the same idea as how many of these are above 100. So in this case, once again, we have the number of subjects, how many subjects scored or waited 10 minutes or longer. It's the exact same number as the previous analysis, because 25 subjects were able to wait for 10 minutes or longer. And then the question now becomes, well, out of those 25 able to wait for 10 minutes or longer, how many of them have a frequency of problems greater than 100, and those are those subjects right there. And if we count up those subjects, we get 14, and 14 divided by 25 gives us 0.56. So the probability that a subject will have a frequency of problem score greater than or equal to 100, given that that subject was able to wait for 10 minutes or longer, equals 0.56 or 56%. So what does this mean? Well, if we go back, we'll summarize it first. So the probability in general that any subject will have a frequency of problems greater or equal to 100, that equals 0.53 or 53%. If we know that they were able to delay for 10 minutes or longer, then the probability that that subject will have a frequency of problems greater than or equal to 100, given that they can delay for 10 minutes or longer, actually equals 56%. So notice these two are basically exactly the same. In general, 53%. Given that they could delay 10 minutes or more, 56%. We'll learn more about statistical error when we get into inferential statistics, but those do not differ with statistical error. And what that means in terms of conditional probability is that your frequency of problems and your delay of gratification are independent. So if the probability of something occurring is the same as the probability of that thing occurring given another piece of information, that means that those two things are independent. So frequency of problems is not related to delay of gratification, because the probability of getting a score of frequency problems over 100 is the same as the probability of that score, given that you already know that they were able to delay for longer than 10 minutes. So as a synopsis of these two analyses, for academic competence, the conditional probability when we added delay was different than the general probability. And that means that academic competence and delay of gratification, they're not independent. In other words, they are related to each other. On the other hand, when we took a look at frequency of problems, the frequency of problems given a delay information, that conditional probability is the same as just the frequency of problem probability. And that means that frequency of problems and delay of gratification are independent. So one of those is conditional, academic competence and delay of gratification. The other ones is independent, frequency of problems and delay of gratification. And hopefully in your mind, you're starting to think of connections. Hopefully some maybe shadow is stirring in your mind, and you might say to yourself, well, this isn't surprising. We kind of already knew this. And we did already know this, because this conditional probability is expressing the exact same story that we saw when we took a look at correlations. So when we took a look at the correlations of this study, we noticed that academic competence was correlated with delay. There was a positive correlation. And those two asterisks means that it's a significant correlation, which basically means that if we ran this experiment over and over and over and over and over again, we would find that academic competence and delay were positively related. So that means that they are significant, and that means that they are correlated. Those two go together. However, if you take a look at frequency of problems, no asterisks. They're actually not correlated. So the lack of asterisks means that if we ran this again, we might get a correlation of minus 0.07. If we ran it again, we might get a correlation of 0. If we ran it again, we might get a correlation of 0.03. If we ran it again, we might get a correlation of minus 0.03. Basically, they're not related, because in the long run, that correlation would be equal to 0. So we already knew that academic competence and delay were correlated. We already knew that frequency of problems and delay were not correlated. Or in other words, academic competence is conditional on delay, and frequency of problems is independent of them. So the correlation and the probability, two ways of expressing the same idea and telling the same story. All right, any questions on that before we wrap up our basic look at probability? Okay, so that's where we're going to end today. So just to kind of put a little primer, a little foreshadowing on what we're going to go forward. These were sort of the basics of probability that I wanted to get down because conditional probability, especially as a psychologist, is very important because that is a lot of what we do. What is the probability that you're going to have this outcome given other factors, right? What is the probability that you're going to be successful in school given socioeconomic status? What is the probability that you are going to have a positive relationship given an abusive relationship in the past, right? I mean, these are the kind of things that psychologists do all the time. So probability is always in there. And it's very important to realize when you're dealing with two variables that are conditional on each other, where given one variable, you get information about the second variable, or if you're dealing with two variables that are independent of each other, because our minds are made to make connections. So oftentimes when things are independent, we start thinking that they're conditional. So it's really important to be able to do those calculations to figure it out and to see if there's actually a relation between the two. All right, so that is all that I wanted to cover for today. So like I said, next time we're going to continue building on this idea of probability. We are getting very close to inferential statistics, which is where the real power of statistics comes out, especially for psychology. But that is all that I wanted to cover today. So I will see you all next time.